Bridge network analysis making use of Thevenin's theorem necessitates we solve for two properties, ETH, the Thevenin's equivalent voltage, and ZTH, the Thevenin's equivalent impedance seen by the load. In this case, our load of interest is element Zx. Let's start by solving for ETH, the Thevenin's equivalent voltage. First, we need to remove our load impedance of interest. In this case, we'll remove impedance element Zx between nodes A and B. Now we need to determine the open circuit voltage between A and B. Note the removal of impedance element Zx has fundamentally changed this complex bridge circuit to a pure series parallel circuit. Impedance elements Zm and N are perfectly in series with one another, as are impedance elements Zp and Zq perfectly in series with one another. The series path formed by Zm and Zn is perfectly in parallel with the other series path formed by Zp and Zq. Nodal voltage A is the voltage across impedance element N. An application of the AC voltage divider rule demonstrates that VA is 57.8 volts at an angle of negative 13.2 degrees. Similarly, nodal voltage VB is the voltage across impedance element ZQ. Application of the AC voltage divider rule demonstrates VB to be 49 volts at an angle of 93.3 degrees. The open circuit voltage between node A and B, VAB, is VA minus VB. Substituting our given values yields 69 volts at an angle of 31.1 degrees. This is our Thevenin's equivalent voltage, ETH. Let's put these values aside and solve for the Thevenin's equivalent impedance, ZTH. Solving for the Thevenin's equivalent impedance, ZTH, also necessitates we remove our load impedance of interest, in this case impedance element Zx between nodes A and B. Solving for the Thevenin's equivalent impedance also necessitates we remove our source. This has fundamentally changed the nature of our original series parallel circuit. This may take some visualization on your part, but the removal of the voltage source by substituting a short circuit has effectively placed Zm and Zn in parallel with one another, and impedance element Zp and Zq in parallel with one another. The parallel combination of Zm and Zn, the simplification I'm calling Z single prime, is 130.1 ohms at an angle of 11.8 degrees. The parallel combination of Zp and Zq, a simplification I'm calling Z double prime, is 110.1 ohms at an angle of negative 68.3 degrees. Z single prime and Z double prime are in series with one another. Our Thevenin's equivalent impedance is a series combination of Z single prime and Z double prime. Substituting our given values yields a Thevenin's equivalent impedance of 184.4 ohms at an angle of negative 24.3 degrees. When bridge impedance Zx is our load of interest, the Thevenin's equivalent circuit seen by the load is the series combination of ETH, the Thevenin's equivalent voltage, at 69 volts at an angle of 31.1 degrees, in series with the Thevenin's equivalent impedance ZTH at 184.4 ohms at an angle of negative 24.3 degrees. All we need to do now is substitute our load of interest, in this case, impedance element Zx. Z load is 270 ohms at an angle of 25 degrees. This simple series circuit is much easier to solve for desired voltage and current figures than our earlier complex bridge circuit. An application of the AC voltage divider rule demonstrates that the voltage across our load is 44.9 volts at an angle of 50.8 degrees. A subsequent application of Ohm's law demonstrates current through our load is 166.5 milliamperes at an angle of 25.8 degrees. These are the same results that we obtained earlier using our delta to Y conversion. I've got a reasonable degree of confidence our results are correct. Take a moment to compare and contrast the two methods. Which method is easier, bridge circuit analysis using a delta to Y conversion or bridge circuit analysis using Thevenin's theorem? The answer is, it depends. Given we had a balanced delta configuration, a balanced Y configuration was super simple to obtain. This may not be the case for all scenarios. This being said, note we had to do an intense series parallel circuit analysis using the delta to Y conversion, and this is only valid for one condition, notably when Zx was 270 ohms at an angle of 25 degrees. The Thevenin's theorem, in contrast, necessitated only two steps, solving for the Thevenin's equivalent impedance and solving for the Thevenin's equivalent voltage. Then it's just the application of simple series circuit properties. In my personal opinion, not only is the Thevenin's theorem a little bit less complicated than the delta to Y conversion, it yields far more usable results. Notably because this Thevenin's equivalent is suitable for the analysis of any load condition, whereas the delta to y conversion was applicable to one and only one analysis scenario. This being said, both methods yielded the same results. Alright, that's about it for now. In conclusion, this lecture examined AC bridge network analysis using delta to y conversion and Thevenin's theorem. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest. We'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.